In this video, we will answer the question, what is a limit? To get things started, we'll ask mathematician Sir Isaac Newton what he has to say. Isaac Newton would tell you that the limit as x approaches c of a function f of x is equal to a limit L if for every greater than 0 there exists a delta greater than 0, such that if the distance between x and c is less than delta, then it is necessarily true that the distance between f and L is less than epsilon. Well, that makes perfect sense. Isaac Newton would probably also tell you that you're going to use limits for derivatives and for integrals. So we better try to understand this definition a little bit better before we move forward. So let's try an intuitive definition. The limit of a function is the height it intends to reach. Focus on that word intends. To a mathematician, a word like intend is unacceptable because it's too vague and it isn't clear what it exactly means. But for our purposes, it's good to get us started. So let's take a look at an example. Let's say we have the function x squared minus 3. So a nice little parabola shifted down 3 units. If I asked what was the limit as x approached 3 of this function, f of x, all I would need to do is think about traveling along the curve as x got closer and closer to 3. Now I can see that the actual height is 6. And as I travel from the left and as I travel from the right, the function always intends to reach 6, and therefore the limit as x approaches 3 of f is 6. That was a function whose intentions were perfectly clear. Let's look at another example where it's not quite so obvious. In this function, I notice that there's a hole in the graph. I'm not going to give the specifics of the function, but f, and ask what's the limit as x approaches 1 of f. I notice there's a hole right there at 1. I also notice that there's a closed-in circle up here at the coordinate 1, 5, which means the actual height of the function at 1 is 5. But what are its intentions? If I look here at 1, and I move along the graph from the left, and I move along the graph from the right, in both cases, it's trying to approach 3. And therefore, the limit as x approaches 1 of f is 3. It intends to reach 3, but its actual height is 5. So this is an unusual function. It's unusual to have a function whose intention is different than what it is actually. Okay, well, what about other cases? Yeah, I'm sure you've heard situations where limits do not exist. Let's take a look at this function as x approaches 1. Here you notice as I move along the function from the left, I'm headed in one direction to one particular point, and as I move along the right, I'm headed somewhere else. We denote these with a little minus sign and a little plus sign in the exponent of the limit. So in blue, I have the limit as x approaches 1 from the left, and I can say that that's 3. And in green, I have the limit as x approaches 1 from the right, and I can see that that's 1. And thus, as Lindsay would say, the limit as x approaches 1 of f does not exist. And that is because the left and the right-hand limits do not agree. The function's intentions are not clear. Let's look at another example. Here we have the function f of x equals 1 over x minus 1. And once again, I'm going to look at the limit as x approaches 1. I'll start from the left. As x approaches 1 from the left, I can see the function decreases toward negative infinity. So I'll write that it equals negative infinity, even though it never reaches it. The limit as x approaches 1 from the right, I'll imagine moving up the function here, getting closer and closer to 1, and I can see it's headed toward positive infinity. And I'll write that it equals positive infinity even though it never reaches it. So here we have a function whose limit does not exist for two reasons. One, infinity cannot be reached, and two, the approach from the left and the approach from the right are not the same. In this example, we'll explain all the different ideas that we've seen so far with limits with one big crazy function. So for starters, let's look at the limit as x approaches -5 for this function here. In order to answer a question like that, you want to go onto the graph and explore around the x value of -5, see what's going on with the function there. So what you can see there is there's actually nothing unusual with this function at that particular point. It's behaving completely normally. And you can see that the actual height of the function at -5 appears to be y equals 3. And there's no holes, there's no jumps. And that means the intended height is the same as the actual height, and that is positive 3. So the limit as x goes to -5 of the function f is equal to 3. Meanwhile, if I ask that same question about this function, but as x approaches -3, I have to think a little harder here. So at -3, I can see there's something unusual going on. So the first question I might ask myself is, what is the actual height at -3? And this closed circle up here shows me that the actual height, which I would denote just with f of -3, is equal to positive 4. That doesn't appear to be the limit, because as I approach -3 from the left, and as I approach -3 from the right, it seems to be zeroing in on a y value of 1, and therefore I can say that the limit is 1. The intended height and the actual height are different. Let's look at another. Let's say I ask the limit as x approached 0 of the function f of x. You can see here at 0, there's something really unusual going on. And I can see that my approach from the left seems to be nearing a y value very different than the approach from the right. And therefore, you can unpack this definition of the limit as x approaches 0, if you wish, into two separate questions. I can ask about the limit as x approaches 0 from the left using a little minus sign, and then the limit as x approaches 0 from the right using a little plus sign in the exponent after the number. So as I approach from the left, it seems that I'm nearing a y value of 1. Meanwhile, when I'm approaching from the right, I'm nearing a y value of 3. And therefore, I can say that this limit, which was as x goes to 0, does not exist, because the approach from the left and the approach from the right are not the same. Another situation where the limit does not exist might be the limit as x approaches 2 of this function. Because the limit as x approaches 2, I can see as I move in closer and closer to 2 from the left, it's getting infinitely large in the negative direction. And as I move closer and closer to 2 from the right, it's getting infinitely large in the positive direction. So this is a function that's diverging toward positive and negative infinity as x gets closer and closer to 2. So I can say that this limit does not exist as well. One last thing that you can do with limits that's pretty interesting is I could also ask a question about a limit as x approached infinity. And I can see here in my graph that as x approaches infinity, the function seems to be settling down, becoming asymptotic, getting closer and closer to a y value of 1. So if we were to ask a question like that, the limit as x approached infinity, the function f, the answer could be 1. So let's go back to the definition of a limit that we saw in the beginning of the video, where a limit as x goes to c of f of x was equal to L if for every epsilon greater than 0, there was a delta also greater than 0, such that if the absolute value of x minus c was less than delta, it implied that the absolute value of f of x minus L was less than epsilon. To translate, this says that we can make the function as close to L as we'd like just by allowing x to get sufficiently close to c. Let's see this with an example. In this example, rather than using a graph, I'll use a table to show what it means to get x sufficiently close to 0 and show where y gets sufficiently close to some limit. First, notice that you can't solve this by substitution. When I plug in 0, I get e to the 0 minus 1 over 0, which is 0 divided by 0, and we don't know the answer to that. So this is a function whose intended value is not the same as its actual value. In the table, I will show an approach towards 0 from the left and from the right. So I'll plug that value of 0 in the middle of the table, and I'll leave a question mark here that's going to represent the limit that we're trying to find. Approaching from the right, I'll start getting close to 0 with positive 1/10. And approaching from the left, I'll approach from negative 1/10. When I plug these values into the function, e to the x minus 1 divided by x, using a calculator, I find values of 0.951 and 1.052. That's a nice place to start. Now I'll look at getting a little closer, both from the left and the right. So I'll look at values like negative 100th and positive 100th. When I plug in negative 100th, I get 0.995, and positive 100th gives me 1.005. I'll creep closer still, trying to get closer to 0. Remember, we can't plug in 0, but we can get really close. I'll plug in negative 1,000th and positive 1,000th. That gives me 0.999 and 1.001. So now it becomes pretty clear what these y values are creeping closer to. The limit to this function as x approaches 0 is 1, because I can see that as I approach from both the left and from the right, I'm getting closer to the value of 1. So to talk about this through the lens of this complicated definition, we wanted x to get closer and closer to 0. Couldn't plug in 0, but we could plug in numbers that were sufficiently close to it. And as we did, we saw that we could get as close to this number 1 as we'd like. That's the epsilon in the problem. If we wanted to get even closer to the number 1, I'd just plug in x is even closer to 0. And I could continue to creep closer and closer to 0, and the y values would get arbitrarily close to 1, and thus we would have a limit. Let's look at one last example of evaluating a limit using a table. Let's look at the limit as x approaches infinity of the fraction 4x minus 1 over x plus 10. Now in this example, x is approaching an infinity, which means there's no way we could actually substitute our value of x since we don't have a number for x. However, we can still think about x approaching infinity through the use of a table. However, x can only approach infinity from one side. It is important if x is approaching a number, like say 5, and you're trying to evaluate the limit through a table, that you consider approaches from both sides of 5, like 4.9 and 5.1, 4.99 and 5.01, and so on. However, with infinity, it is obviously sufficient to just consider values of x that are increasing in magnitudes. So powers of 10 do a good job. We can approach infinity by plugging in larger and larger values of x, 10, 100, 1,000, etc., until we get a sense of whether the outputs are getting closer and closer to some particular value. So when I plug in 10, I get 4 times 10 minus 1, which is 39, and 10 plus 10 is 20, and 39 divided by 20 is 1.95. That's pretty close to 2. Maybe the limit is 2. So we plug in 100. 4 times 100 minus 1 is 399. Divided by 110 gives me 3.63. Okay, maybe the limit isn't 2. Let's plug in 1,000. 4 times 1,000 minus 1 is 3,999. Divided by 1,010 gives you 3.96. Do you have an idea what the limit might be now? If so, let's see if when we plug in 10,000, if your intuition is confirmed. When I plug in 10,000, I get 39,999 divided by 10,010. 3.996. At this point, I think it's pretty clear that our limit as x approaches infinity is 4. And if we think about our definition, we can make the function as close to 4 as we want just by allowing x to get closer to the value of c, which is in this case infinity. As x gets larger, we can make this function closer and closer and closer to 4. And if you're wondering why that is, it comes down to the fact that the ratio of the largest degree term in the numerator to the largest degree term in the denominator, 4x divided by x, is 4. So for sufficiently large values of x, the -1 and the +10 have really no effect on the fraction. 4x divided by x is all that essentially matters as we get closer and closer to infinity. And this is the idea that mathematicians were trying to convey when they came up with this very complex definition of limits.